Hello, and welcome back to Calero Academy. Today, we will be investigating what happens when a cube melts in a glass filled to the brim with fresh water. Now, three things could happen. Number one, the water could overflow and run off the edges. Number two, the water level could just stay the same. Or number three, the water level could decrease. Now, to solve this problem, we will be involving some constants. We can have V sub c and M sub c be the volume and the mass of the cube, of the ice cube, before it melts. And we can have V sub m be the volume of the cube, of the ice cube, after it's melted. So that will be the volume of the water that came from the ice cube. And of course, the mass of that will remain the same. So, before we go on, we can get a feel for the question by investigating two other possibilities. So we have two other glasses, and we're going to look at some other cases about this ice cube. We're going to look at extreme cases, and then from there and make an educated guess about our case over here. So suppose that we have an ice cube floating magically above the water, or we could imagine it suspended by a stick. So when that melts, what will happen? What happens will be that the water will obviously overflow, because we're assuming that it's up to the edges. The water is perfectly filled, and so when this melts, the water will come down and it will overflow by a volume of V sub m. Now, let's look at another case. Suppose we have a stick pushing down on another ice cube. So we have an ice cube completely submerged in water, and the glass is again completely full. When that melts, what will happen in that case? In this case, the water level will decrease because ice is less dense than water. And hence, when it melts, it will leave more volume than it will replace, and hence the water level will sink. Now, let us apply Archimedes' principle. Archimedes' principle states that the mass of the volume of water displaced is equal to the mass of the floating object. So, from these two extreme cases, by the way, we can also make a guess that when this melts, the water level will stay the same. So we can use that as our guess, and we'll show that that is right with Archimedes' principle. So, what we're going to do to find what happens is separate what happens into two different effects. So first we look at what do we gain. So how much volume do we gain? We gain obviously V sub m from the cube. So when the cube melts, we get an extra volume of V sub m. Now, what do we lose? Well, we lose P sub O times V sub c, where P sub O is equal to the original density, which is equal to M sub c on V sub c. So that's the density of the ice cube before it melts. So what this is saying is that we are going to be losing the volume of the ice cube that is below the water level. So what we're really doing, if we redraw our first case over here, so what we're doing is we're dividing our effects into negative. We lose all the volume over here, but we gain this volume plus this volume once it's turned to water. And it turns out that these two effects perfectly balance out, because P sub O times V sub C is equal to V sub M. And we can see that after we plug in some numbers. Because P sub O is equal to M sub C on V sub C. And also, of course, if we look at the final density of water, the density of water we define to be M sub C on V sub M, which will equal to 1. And it's M sub C because the mass of the water will remain the same. So after a little bit of number shugging over there, we will get that P sub O times V sub C is equal to V sub M. And therefore, these two effects perfectly cancel out. And therefore, the change in water level will be equal to 0. Now, let's look at another way. Let's look at another way to look at it. So, what we're going to do now is put all these cases, case 1, case 2, and case 3, on a graph. So, our y-axis will represent the amount of water that is spilled, either 0, or some spilled, or the water level decreases. And this will represent the forces on this ice cube. So either it could be being pushed down, like in this case, or it could be held up, like in this case, or it could be perfectly 0, like in our natural case over here. So, in this special case where we're dealing with perfectly fresh water, we have that at our 0 point here, that when the forces are perfectly balanced, when there's no artificial forces acting upon an ice cube, it turns out that the amount of water spilled is perfectly 0. And we also know that when it's being held up, there will be some water spilled, and when it is being pushed down, there will be a decrease in the water level. And so all these will lie on a line. And we can define this net change in the water level as being equal to the percent of the volume that is submerged percentage of the volume that is submerged sorry about that. The times minus 1 plus V sub M, or to rewrite it nicely, the net change n sub n dot c is equal to V sub M, which is this guy over here, minus the percent of the volume that is submerged. And we can see that this is true because, experimenting with our graph over here, we have that 0% of the volume is submerged. And therefore, the net change in volume once it melts will be V sub M. And over here, we have that 100% of the volume is submerged. And therefore, we have that we have that it is V sub M minus V sub M minus V sub C is the amount of change. And since V sub M is less than V sub C, the water level will decrease because over here we'll have a negative number when we plug it into our function. And this is going to be the end result of our work. And that ends this very nice, quick and short Calero video. We hope that you enjoyed this video. And if you have any comments, or if you wish to add anything, or if you find an error, please put it down in the comments section. So thank you again,